Hello and good afternoon to everyone joining this webinar of our focus on geothermal energy for the weekend webinar series, a partnership between Enerchange and ThinkGeoEnergy. My name is Alexander Richter, the founder of ThinkGeoEnergy, and with me today is Jamie Airnes, the CEO of HydroVolve, a company working on unique downhole technology for wells with an increasing focus on the net zero energy industry. Jamie will discuss about his company's technologies and percussion-enhanced drilling technology and how it impacts the drilling performance. We will have the opportunity after the presentation to ask questions in the panel that you have access to in the system. We will group these questions and try to get to as many questions as we can. With that, I'm handing over to Jamie. Jamie, the floor is yours.
Thank you, Alex. Good afternoon or good morning to everyone, depending on which part of the world you're joining us from today. Happy New Year to you all. And thank you very much for the opportunity to speak today and hopefully engage later on in the Q&A session. So my name is Jamie Airnes. I run a company in Aberdeen called HydroVolve. And today I'd want to take a few minutes. It's a short presentation, maybe 15 or 20 minutes or so, and just to talk about some new technology that we're introducing to the drilling space, particularly for geothermal applications, and run through what it's all about and what it can do in the future. So like I say, new technology being introduced to the drilling space, record-breaking technology, I'm pleased to say, through our trials that we had in 2023. What is it? The system itself is a percussion-enhanced rotary drilling system. Like I say, we trialed this earlier in the first half of 2023, multi-operator campaigns throughout continental Europe. Terrific results in the first instance. We've drilled 2 times faster, we've drilled 3 times further, and we've proven this in deep, hot, hard rock applications, the type that are synonymous with geothermal industry and the challenges they are involved. Our system itself is plug and play and can be used and introduced into any conventional drilling system. What we have and what we believe we have is something that is quite unique and really can be transformational in terms of looking at project economics and geothermal drilling applications. What does it mean, and what does it mean for geothermal drilling and for the industry itself? Well, if we take a high-level overview and holistically look at different systems, different energy sources, the levelized cost of electricity, the LCOE for geothermal is about $56. If we look at solar, it sits at around $51, and for onshore wind, it's $52. So fairly competitive overall, holistically. A large component of that, like any drilling application, is the capex of drilling itself, and it's a huge contributor of that overall cost, the LCOE, attributed to geothermal wells themselves. It's 30, 40, 50% of the capex that's required on a project basis. And if we look at the future for geothermal, when we talk about the ability to unlock the potential on a global scale, we're into systems like EGS and AGS. And from a capital intensity perspective, they are actually more expensive, currently residing around $100 per megawatt hour there, which is a huge capital contribution and component of the overall cost. The drilling contribution there is about 75%. So it's a huge cost, but you can also look at it as a huge opportunity to drive that cost down and move the dial to the left. And what we're trying to do is to make sure that it is attractive, it is investable, and we unlock the potential of those opportunities in particular. Make it available for everyone on a global scale, anywhere. And we want to be able to do that. We want to be able to scale up, but scale up at pace. So how do we reduce the drilling costs themselves, those huge capital contributions of any given geothermal project? Well, time is cost. Anyone that's been involved with drilling operations knows that time is money. That's the equation. And you overall have to reduce the time it takes to drill the well. That's where you can make large differences in terms of project economics. So how do we do that? Drilling faster, that's the most obvious place to start. Increase the rate of penetration, the drilling speed when we're on bottom making hole. A couple of other things we can do, but one of the dominating features is to increase our bit life, to stay on bottom drilling, to reduce those flat spots, to reduce the tripping time, and reduce our tangible costs that are associated with the drill bits themselves. Conventionally, if we run a choke model on the cost of drilling, we think in drilling we're maybe impeded or limited by formation evaluation in terms of how fast we can go, or perhaps it's cuttings handling that's slowing us down or restricting us. Contrary to that, in geothermal, we think about, well, it's hard rock, it's that hostile environment that's providing these classic drilling challenges that are making it more expensive to drill the wells. So what's percussion-enhanced drilling? What does it do for us? How does it work? Well, it's not new, and it's not HydroVolve's hypothesis that it works and it can allow you to drill faster. A quick literature search will return, dozens of examples, SPE papers, and working examples from operators where it's been incredibly successful in terms of improving that rate of penetration. What is it? It's just a rapid hammering action, that sort of point loading and crushing of the rock, pre-fracturing the rock ahead to allow the drag bit to be more efficient in its cutting mechanism, the way it drills hole. And like I say, it's been used effectively in the past, over decades actually, to increase drilling ROP by several factors. We're not talking marginal gains here. These are step changes in terms of performance. It is widely practiced. It's used along the world, offshore, onshore, throughout really. But it can be difficult to achieve. There are some unique challenges with it. The systems themselves can be expensive, they can be complex, expensive to build, but also expensive to service and repair and maintain. And they have some unique impediments and challenges as well about the reliability of the systems, the power management, the ability to have the pressure that's required in these systems, and also can induce well management issues as well, working at depth, hole conditions, etc. So a few challenges and impediments that have classically perhaps held back the advancement and the mass adaptation of percussion drilling. So what are we doing? Well, it's classic rotary drilling, really, with a percussion enhancement. It's as simple as that. It's not vibration assisted, not like some of the other technologies you might have seen in the past that are related or have provided step changes in drilling performance. This is axial vibration that we're using to enhance the drilling performance. This impulse, this additive weight on bit that we use to pre-fracture the rock, to increase the depth of cut, to keep that consistent, to keep the bit engaged. And what that does is it reduces some of the classic dysfunctions that you would see in drilling, the bounce, the chatter, the whirl. That in turn creates a nice environment for the drill bit to perform as per its original design intent. So we can reduce the wear on the cutting structure itself, and we can create a lower impact to the drilling system and the drill and the BHA as well. What are we trying to do? Increase ROP and increase the bit life. We want to create that environment to allow the bit to perform as it was originally designed to do, per its design intent. What does our system look like? It's quite simple. Actually, it is plug and play. It's about 10 feet, 9 feet, 10 feet in length. It can sit directly behind the bit. It is plug and play. It's hydraulically powered by the drilling fluid, whether it's water-based, oil-based, pure water, aerated systems. And it operates automatically. Basically, as soon as you want to drill ahead, as soon as you're pumping, then the system kicks in and we're operating. Interestingly and quite uniquely, we're full through-bore access. We don't induce pressure drop. We're not taking away and adding parasitic pressure losses to the system overall. It's negligible in terms of what we have from a pressure requirement. And we're full metal valving. So we're ideally suited to be deployed in these hot, hostile environments. Simply, it's premium connections, top and bottom. At the bottom end, we go directly onto the bit. Like I say, we can go elsewhere in the BHA, but classically, and certainly until now, we've been deployed directly behind the bit to provide that axial motion, that incremental weight to the bit. It's a telescoping bit sub that we have. At the top end, we have a non-rotating sleeve that allows and provides the opportunity for our valve assembly, this infinity valve assembly that we have, that really is the operating system of the tool itself, rotating valve assembly, driving a piston straight onto a hammer, an anvil, and then onto that telescoping bit sub and directly onto the bit to provide that accretive weight on bit and point loading that you require. So what did we do in 2022 and 2023? Well, we're quite privileged here at HydroVolve in Aberdeen. We've got a tremendous facility at Dice near the airport here. We've got a state-of-the-art test facility. So you can see in the picture there, that's a 20-meter test bed with a horizontal drilling rig in place with a GeoVolve HYPERDRIVE there. We got a 5,000 PSI test loop, Gardner Denver PZ9 pumps, a Caterpillar 1,000 horsepower engine, and twin HPUs. We can rotate our drill string at about 130 RPM for test purposes, and we can push and pull over £1 million worth of load. We're fully instrumented, fully automated. We can monitor, capture, record, and crucially, we can witness any of the testing and qualification that we do as well here in Aberdeen. So we embarked on a series of tests late in 2022 and early in 2023, whereby we started off just very simply understanding the output characteristics and capability of the tool. And then we moved on to a series of drilling tests themselves, using a variety of third-party bits, PDC bits, to drill out cement, mock conglomerate, and ultimately we drilled granite. Good old Aberdeen Rubislaw quarry granite in 3-meter sections, very high compressive strength, very low fracture network, to complete our trials. And what we've got in the pictorial before is just showing the difference really between conventional rotary drilling, same parameters, same weight on bit, and just toggling the system between hammer on, hammer off, hyperdrive on, hyperdrive off. And what we witnessed was very, very similar to much of the literature that we had reviewed and the performance gains that we were hoping to see and expecting to see. It was a direct correlation, very, very prompt, very obvious, where we got a step change in the ROP when we were drilling this granite. As soon as we turned on the GeoVolve HYPERDRIVE, we saw that step change in improvement performance, 2-3 times as fast as we were drilling with the same parameters in rotary mode. So very, very encouraging, tremendous results really. Moving on to the field, the initial field trials. What we've done early in 2023 is we've had multiple trials with the operators in continental Europe. We've used the sizes that we currently have available for 6-inch drilling, 8.5-inch drilling, and 12.25-inch. And we've had some really fantastic results. The fastest ROP ever recorded in a prolific drilled basin. We had the longest drilled interval ever recorded in that extensively drilled basin. We doubled the ROP average across the field. It's a field where they use multiple technologies that people would be very familiar with, several tier 1 bit suppliers, so very, very pleasing. And we also tripled the average distance that we went across that field. So we went faster and further. Looking at one of the field trials, technical performance in particular, I I will place some compliment here to some of our peers that have helped us. We talk about the performance of the drilling bit itself. We work hand in hand with a company called Zerdalab with Vasily and his team there. And in tandem, we produce tremendous results across the board here from a technical performance perspective. Flow durability and our resilience was over 350 hours circulating with a fairly high density mud, 2.1 SG in a single deployment, top to bottom. We were almost 30 days on bottom at bottom hole temperatures, static temperatures of over 220 degrees C. We drilled for over 250 hours, single run, with a tool at over 220 degrees C. We evidenced tremendous durability from a tool performance perspective, drilling over 600 meters, shoe to shoe. The best offset was just over 200 meters in that area. And very pleasingly, we also took on the challenge from that shoe to shoe drilling campaign of drilling out the shoe track itself. And I think that was drilled in record time. I do accept that some of the purists amongst us may say that's not always a good thing to drill shoe tracks so quickly, but it's in the books now. And like I say, we proved the capability of our own drill bit design that we developed exclusively with Zerdalab, a PDC drill bit there. Moving on to case studies expressly that we carried out in 2023 as part of those trial wells, just to give a sort of flavour and insight as to the sort of challenges that we had. Here we're very deep. We're over 6,000 meters. S-shaped well. We were in the vertical component towards well TD. Low inclinations between 10 and 20 degrees. And interestingly enough, very contrasting lithology, quite challenging, from shale sections to sandstones and limestone stringers. So interbedded formations, it's a classic question we get, is how do we perform in interbedded formations? Well, this is a working example, a challenging environment where we did very, very well indeed. Shales of very, very low compressive strength up to these sandstone cleaner reservoirs at 20, 25, I think even 28 kpsi were encountered. So that was the challenge. What did we do? Well, the first thing we did before we embarked on the project is we asked the operator to define success. What does success look like? And they provided us with 25 of their best analog wells in this basin. It is a prolifically drilled basin, I should say. It's a continuous campaign. And we were asked to perform this 6-inch drilling trial here early last year. And success was attributed to a single run that would be of 100 meters run length and at about 1 meter per hour. Slightly better than the field average. If we look across the base axis, we can see that the ROP going from 0 to 2 meters an hour and the run lengths from 0 to 230 meters. The average is about just under 1 meter an hour in this field, and they do about 70 to 80 meters. And what we can see is that that we've exceeded even the operator's expectations and perhaps our own for a first run, to be honest. We set out with the design engineers with the intent of saying, what does our own internal success look like? And we coined the phrase double. We thought it'd be good to double the ROP and double the average run length. And we've exceeded that in terms of the run performance here. So the hyperdrive being placed at the top right-hand corner, illustrating the performance of the system itself. It's a system approach we take. We use the hyperdrive and the terabit itself. So phenomenal performance, a field record in terms of straight line speed, ROP, but also in terms of endurance and durability, setting that field record for distance drilled. Anyone who's been involved in drilling deeper wells knows that actually on bottom drilling can be your sweetheart. You can lose a lot of time, money, and be somewhat frustrated if you're tripping. So actually that's why the operator was looking for longevity and run length rather than just pure straight line speed. How does it translate for that operator in this application. While the 6-inch hole, our run rate that we had, we would have saved them on a time basis over 7 days. But crucially, and as I alluded to in the previous slide, the overall time saving, because we're on bottom and continuing to make forward progress, was almost 20 days. We've saved drill bits, and overall, we've slashed the cost of that section. So over $1.5 million for that operator. A pretty impressive trial, I would say, by anyone's measure stick. So what have we got? Just to summarize, we believe we've got technology for today. We've spent a lot of money, we've invested a lot of time and resource developing, designing the technology, testing the technology, and then piloting in these trial wells this new technology. It is novel, it is unique, we believe. It's a percussion-enhanced rotary system. Excellent fuel trials performance. Like I say, drill twice as fast, 3 times as long in the deepest, hottest of hard rock applications. We can plug and play into conventional drilling systems. There's no electronics. There's no other control systems required. Standard conventional rig applications here. And we genuinely believe that we can provide that transformational change in terms of geothermal project economics. Thank you very much.
Thank you, Jamie. Very, very interesting. And I see here that we have a lot of questions dripping in, but I'll maybe start with a few, let's say, more general and questions and naive questions on my end regarding the subsurface. And of course, you know, geothermal differs quite greatly from let's say the hot regions, volcanic regions, to let's say quick granite conditions and sedimentary conditions. There are quite some differences, and of course I would assume kind of also differentiate kind of how quick you can drill through it. But kind of what impact does the actually temperature play in the sense of getting as quickly as possible ahead in drilling? Did you study that in a sense of how that impacts it, and to what degree?
In terms of what it means to the rock and bit interface, or do you mean in terms of the tool's performance itself?
So basically subsurface temperatures. I mean, like, of course, I mean, if you can drill into, let's say, very hot regions, kind of where you have 200-300 degrees Celsius and more, versus, let's say, lower temperature resources in the context of, let's say, heating projects that maybe go down only 1,000 meters and have 30 or 40 degrees. Yeah. And what's the correlation? How on the speed of drilling in that context, of course, apart from the geology itself?
Yeah, so looking at a literature search, for us, we're comparing ourselves on a side-by-side basis versus the other technologies that have been deployed in similar areas to date. And really for us, it's about the rock strength itself at the depths that we've been at today and the temperatures we've been at today, not so much the temperature itself of the rock. It really has been about the rock strength itself and the physical, petrophysical properties included of the rock itself, the porosity and density of the rock. But we're always comparing ourselves on a side-by-side basis by what's been done to date. We've not got to the position where we're extending the boundaries and moving to supercritical, for example, or 350 beyond. We're not there yet.
But there could be, let's say, a challenge, like if it gets too hot, that then kind of from a material perspective, your technology could face challenges if it gets too hot.
100%. You're absolutely right. We're using, you know, classic steel that you would see in any oil field BHA. So, you know, we're using 4330V steel for that, and the mechanical strength for that starts to drop off from a performance perspective around about 400C. So what we're saying just now is that the tool is very, very comfortable and capable up to about 350C, and that's what our design has been based around. What I would say about that is that any other component in the BHA will be in the same position, so no worse off. And if we look at that from a choke model perspective, we're very, very similar from that perspective. But crucially, our tool, in terms of a output characteristic and performance capability, will not see any performance drop off. So if we look at other systems that might be out there that are relying on elastomers, for example, for performance, you would see perhaps a compromise in the performance or an inability to perform at these higher temperatures. That is not the case with our tool.
Okay. All right. So let me jump into the tons of questions that people put in here. So, and I mean, I might not be the right person to group them correctly, whatever. So maybe exclusive that some of these things maybe are too similar.
Yeah.
But
for me.
Yeah. So I'm trying my best. But what I would say, maybe, like, because there's quite a few questions, like if you keep your answer relatively short, so we can fight through this a little bit. So first question, what's the upper limit for the rock compressive strength that you can use PDC bits on?
Yep. So what we've seen and what we've tested today is up to 35 KSI. In terms of absolute strength, I think I'd have to defer to our experts in our bit design world for that. So that's something I can definitely come back to you with. What I can say is that in terms of impact resistance and performance of the PDC cutter itself, we are at the lower echelons of what they are capable of overall in terms of their wear and impact resistance. So we're very much at the lower operating end of what they are capable of, and we're drilling up to 35 KSI just now.
Okay, then.
But I'm happy to take questions offline and try and provide a more detailed response from our experts that we work with. You'll understand I'm not a bit designer.
No, so we have, I mean, like I said, I mean, Jamie is on LinkedIn, and you can connect with him there.
Yep.
But so it should be easy. All right. So then here another question here of an actual convert to your technology, but asking here if you could outline maybe the major unique selling points over fluid-powered hammers and air hammers, and it would also be helpful to hear the level of ROPs you achieve in the comparison with other bit systems.
Mm-hmm. So fluid hammers themselves, I mean, essentially what they're using, they have a high parasitic loss. You've got rotors and stators and cam systems in there. So you've got a higher parasitic pressure loss. Capitally, they're quite expensive to build, and the maintenance and repair can be damaging as well. So one key difference there is the reliability and survivability and the use of elastomers within. So clear challenges there when we're operating at temperature. Fluid hammers themselves, they deliver the axial impact in a slightly different way to what we are doing. We're using less static weight on bit. We're directly engaged with the bit, and we're pulsing to provide an incremental weight on bit to pre-fracture the rock. Whereas there's some axial movement there with a cam system that is dropping and directly hitting on top of a bit, not always with the bit fully engaged and profiled to provide the point loading on bit. So it's kind of moving in between compression and tension and not really knowing where you are at any one given time.
Okay.
So for fluid hammers, for air hammers are tremendous performance and used extensively on a global scale, but a few challenges. They can be expensive. The spread required to rig them up can be prohibitive and challenging. It's a big footprint, big environmental impact. And of course, you may have to choose, depending on what depth you're going down to, you may have to flip between air systems and fluid systems. So you're committing yourself to those setups and changeouts as well from a hammer system. So some challenges at depth, and if you want to use a fluid system, or indeed you have to use a fluid system at some point, then you're committing yourself to a changeover. So both systems have their relative merits, but we think we've got a distinct competitive advantage because of our simplicity and the fact we can just plug and play.
Okay. All right. Oof, the questions trickle in here, but on the lab test slide, it looks like the hammer bit performance is increasing with time. Is it possible that there is a pre-fracturing below the drilling phase that then is accelerating the ROP?
It looks as if it was fairly consistent actually across the board. We repeated this test multiple times, and I should say we also did it in front of clients, which was an exciting experience, I would say. But yeah, I mean, the rock itself is not entirely homogeneous. It's granite rock. It is a low fracture network. It's a high compressive strength. but the step change in performance between toggle on and off was quite dramatic. It was fairly consistent. The LPs did move up and down to a certain extent. All I've provided there is a snapshot, but happy to provide full reports for anyone that's got interest.
Okay, then here another one, and I'm trying to kind of answer questions from individuals here that, because many have asked several questions, so I'm trying to kind of at least go fairly through them. Names here, do you have any well path diagrams for these wells?
The short answer is yes. So, but where the more extended answer and helpful answer is that we've been in vertical holes, we've been in S-shape profiles, particularly in the area where we're returning to the vertical, and we've been in tangent sections, and that's pretty much where we're going to play in the next 6 months. So we've been deep, and we've been in S-shape. We've actually been in J-shape wells as well, vertical wells and tangent sections.
Here a bit of a question. Yeah. Were there any negative events or performance observed? Or let's say, have there been some challenges that maybe not resolved yet? Yeah,
not that they've not to be solved yet, but this isn't new. We've been working on this for a period of time. What sort of challenges have we had? Very, very high level. From a material science perspective, looking at different finishings and coatings to make sure we do have that endurance and reliability and survivability. So we've done a lot of work in the material science space. Mechanical strength, clearly we're in a very hostile environment. If you're at 6,000 meters and drilling with spaghetti 3.5-inch pipe, you're in quite a challenging environment. So we've done a lot of work looking at our own connections and proprietary connections there to make sure we have the right strength in the tool. Simple things like looking at the geometry of the non-rotating sleeve, the suitability for drilling casing shoes versus drilling open hole, different types of rock, and different challenges like hole enlargement or washout areas. What happens then? So we've done a lot of work on our non-rotating sleeve, the geometry of it, the contact forces, the materials we use, etc. And probably one of the biggest things, took a lot of time, a lot of help from our friends at Zerdalab, was understanding the output characteristics of the tool and looking at the bit to tool to bit interface. So how do we interact? How do we perform? And actually making sure we have the bit that is matched to the output characteristics. That's probably the thing that we've worked hardest on as a collaboration. So yeah, there's a few things you'd expect with the evolution of any young technology.
Yeah, here a question, a little bit summarizing maybe some of the questions asked here. If your technology has been tested with some of the logging and measurement tools while drilling, and has there been any interference or has affected the life of the tools?
Yep, so we have been in the survey tools. We've not done LWD FE yet. We are being pushed in that direction and will happily be led there this year with operators and a tier 1 service provider. What we have done to get ahead of the game there and to understand the relationships is we have dynamic sensors that we use, and we put in the bit directly or actually in our bottom telescoping sub. And then we also put them at the top of the tool so we can understand exactly what is going on around the drill bit to our tool interface. But crucially, and this I think is where the question alludes to, is what's happening at our top sub and behind us. And the results there basically tell us that we're bang in the sweet spot. We wouldn't have any problem interfacing or interfering with any of the survey tools or indeed any of the drive systems that sit behind us.
No. Simple question, kind of, have you done any directional work, so directional drilling with your tool?
No, not yet. And just answer to the previous question, that's one of the places that we'll be going in 2024, and we'll either sit directly behind the bit, or in the case of RSS systems, or more commonly in any steering system, to be honest, is we'll sit behind the steering head, the steering system itself. So again, we'll understand the interfaces there, and we'll have to tune our tool to make sure we have the right output characteristics depending where we sit on the BHA. Looking forward to working with the operator in question there specifically, and obviously that large tier 1.
Another one here, has resonance been experienced in the operation of the system, and what harmonic modeling is conducted to prevent this from occurring?
Yeah, so big challenge for anything in industry, anyone that's got BHAs, is to make sure you're not contributing to HFTO. It's an interesting question because, you know, one of the first things you can do to make sure that you're not exposing yourself to that is make sure you've got the correct bit to formation interface, and that's all about engagement, and that's exactly what our tool does. We work with a very low static weight on bit classically, and we provide the incremental weight on bit through the axial motion through a telescopic sub to make sure that the bit is fully engaged in the formation. So we're not exposed to chatter, which then induces whirl, which then gives you the challenge from the resonance and HFTO. We also have some tools in our inventory. We are tunable, so we can change the frequency of our tool so that if we do get any signals, if we do have any concerns, then we're in a position where we can change the parameters and change the frequency without necessarily compromising the drilling performance. Hope that answers.
Then here, rate of penetration. So the question basically, you know, what are PDC in granite? And here's the particular question on the estimate in granite, such as Aberdeen granite, for example, which would be typical for geothermal projects.
Typical ROP, it's difficult to answer because the fracture networks are very different. The compressive strengths are very different. We always compare ourselves on a side-by-side basis. And what we can say is to date, we've outperformed what the competition has been doing. There's lots of work that's been done in terms of hard rock drilling, granite in particular with PDCs. The biggest evolution in terms of bit performance is all around PDC survivability and endurance in these hard rocks. So all I can say is we've had a step change in terms of being compared on a side-by-side basis. And so far, we've produced orders of magnitude 2-3 times faster. That's not to say that's the limit. Let's hope we can do better, but you know, respecting where we are today.
So, like I said, I'm trying to kind of maybe don't sound too stupid with some of the questions, but let's do it. Yeah, does the frequency of the tool change with flow rate? And if you increase the flow and pressure, could you create so much impact that you destroy the buttons of the bit?
Yeah. So it doesn't. It changes with rotation. So it changes with rotation. There's a few things that are going on, but at the highest level, it's the amount of valves that we have in our drive system. It can be anywhere between 4 valves up to 16 or 24 valves. So we operate typically at a range of between about 4 hertz up to 40 hertz. Is it controllable? Yes, it is. It's controllable at surface by changing the surface RPM.
Okay.
And actually, there's a few preservations that we can do in terms of destroying PDC cutters, because that's a classic question. I think I mentioned earlier, we operate at the very lower echelons on that envelope of what the impact resistance is for the PDC cutters that we choose. We're in or around 10% of what they're tested to. So to give people some comfort in terms of margins of safety, we're at the lower end. We also have some features that work in our favor. So I talked about a telescopic bit stub that we have. We can only extend so far. And obviously our tools, we understand intrinsically what the output capability is of the tool from a system perspective.
Okay. Here a question of someone that's actually interested in your system. So I'll share the details with you, but can you alter the hammering frequency, and how can the frequency be changed with a mud flow, for instance?
Yeah, so I said before, but it's surface rotation that will change it. We can change the setup in terms of the tool itself from a valve array perspective, but really you have an operational flexibility by changing the surface RPM. Sorry, what was the second part of the question there, Alex?
The question was if the frequency can be changed of the hammering,
yes,
and with the mud flow, for instance.
Yes, absolutely. So we can change the impact force by changing the pressure drop across the bit. How do you do that from a practical perspective? We change the flow rate. So we can do it pre-deployment, and we can also do it while we're in hole in responding to particular formations or challenges just by playing with the flow rate. And just to remind, we're full through bore. We do not have a parasitic pressure loss through our tool, unlike other systems. We simply rely on the DP across the bit, which comes from the nozzle.
Okay, and we will take the whole time, Jamie.
That's okay.
Here is, yeah, no, I think it's great to see the interaction. So we start again from the top. Does the axial vibration decrease the life of the measuring and logging tools?
Yeah, so I think I probably just touched on that earlier. It is very passive in terms of lateral vibrations, primarily because of the stabilized nature of our assembly, but also the extended gauge bit that we have. So from a lateral perspective, we're in good shape. Axially, without giving too much away in terms of the secret sauce that goes into the tool, we are actually moving hundreds of millimeters up to maybe 1 or 2 millimeters to provide that constant depth of cut and bit engagement. And crucially, as I mentioned before, not only have we tested this in our own rig, which is fully instrumented, we've tested this downhole with dynamic data sensors in full capture mode and done the analysis post-drill. So we can say with some confidence that at the top end of the tool, the energy has dissipated. It's all going directly in front and through the bit into the rock. Okay,
here that's actually a question that we've asked tool providers before. I think a very good one. How when you drill in remote locations, how can the tool be addressed to the relatively field, or how can you get it to the field relatively quickly?
We've operated so far remotely in some of the most challenging environments you can imagine, to give you some confidence. It's a very, very simple tool. It can be pre-set up from Aberdeen, from our workshop. Service and repair is fairly simple as well from our perspective. So we don't need too much specialized equipment or service capability from a facilities perspective. So it's pretty simple, and we do. It is we have done remote operations absent of personnel at the rig. We've done it monitoring the data live with our tech support that we have here in Aberdeen, and also with Zerda Lab as well. So pretty simple tool, and from a service and repair perspective, it's very, very simple as well. So we've turned these tools around out with our facility before.
Okay, then here the question, is the tool always on, or can it be switched on and off from the server if required?
Yeah, to all intents and purposes, it's always on. It's always on.
Okay. What kind of deviation do you experience drilling at these rates?
It's a great question. So we set ourselves up because we're in tangents or in vertical wells, classically for a hold. You can tune your BHA to any performance that you would like, whether you want a drop or a build. One of the things that's in our favor, if you think about trying to maintain verticality, for example, that was the challenge on the case history that I showed. When you're deeper and you're trying to stack weight up to be able to give you the drilling performance, you can deflect, particularly in smaller hole sizes with skinny pipe and skinny collars, you can experience deflection. That's working in our favor here because we require less static weight on bit. So you do not have to have the heavy BHAs, and you do not have to slack off and cram weight on and deflect your BHA. So actually, it's much easier for us to hold inclination when we're drilling ahead, because just to remind, we're using the incremental force that's generated through the tool itself directly at the bit. We're not slacking off weight from above. We're using half of that.
Next one here. What do you consider the impact force on each blow?
How do I consider it, or
what do you consider the impact force to be?
Well, we know exactly what it is, and we can tune and tailor it. There's a couple of things that we can change. So what we do is we look at the application itself. If we have real data, so maybe we have sonic and density data, and we know what the compressive strength of the rock is, and it's homogeneous. We understand the highs, the lows. We can tune the tool specifically to provide the output force to match that application. But we also have the ability to tune that at surface by changing the flow regime as well, to change the output force. So we test, we know absolutely for a certain pressure, for a certain setup that we have inside the tool, what the output force characteristics are, and we have the curves to match that. So that's part of the pre-job work that we do in advance to make sure it's set up appropriately and accordingly for your specific application. It's very simple to change, but that's the work that we do at the front end, and we would encourage any operator to engage with us early and provide us with as much technical information, operational information as you have, so that we can work together and provide the right setup for the tool to give us the best chance of success.
Do you need or recommend a shock absorber to be run above the tool to protect the rest of the drilling string?
Probably covered that before, but it's fairly benign behind us, so nope, it's not required, and we wouldn't recommend one.
What's the deepest geothermal that you actually used for the technology, and what was the hole size?
Deepest we've been so far, maybe slightly, but I want to say it's 6,200 meters, and that was in 6-inch hole. The hottest we've been at so far is 225 C. The hottest recorded, I should say. Yeah. Hottest recorded. Yeah. There's been a geothermal well that has very high temperatures, but unfortunately we don't have that temperature data for the bottom hole at that point. So yeah, 225 is the hottest we've been in so far. The deepest we've been at is about 6,200 meters.
That's quite something. So yeah. What size bits are compatible with the system? What's the largest that you could use?
Okay, so we currently have an 8-inch, 8¼ tool that's going up to 12¼ or oddball sizes. You could do 13½, 14¾ and so forth. Beyond that, we would want to introduce a larger tool. We have a design on the board for 11-inch, 11¼ tool, so we'd be able to cover 16-inch, 17½-inch. The beauty about this tool is it's fully scalable. So if you have an application, we've been speaking to clients, for example, drilling 20, 24-inch, where it's very, very hard rock directly from surface. So think about volcanics, for example. So it's fully scalable is the answer. What do we have commercially available today is 6¾ tool, 4¾ tool, and an 8¼ tool. So we can go from 5 7/8, and that's a deployment we'll be doing in the second quarter this year, right up to 12¼ and these are deployments we've already had. So conventional oil field sizes, very familiar with. We can support your opportunity, and if you have anything specific, we'd love to hear about it. Our capability here in Aberdeen is design, prototype, manufacture, test, qualify. We do it all in-house. So if you've got something unique, something bespoke, we've got the support that can help you here.
Okay. Do you see an overall drag reduction in the drilling system with the percussion action?
Yeah, it's a good question. So we do think you get a little bit of drill string mobility in there. It's not a vibrational technology like be careful, agitating type technologies. So we're not providing that classically, but what we do is because we are constantly engaged, we tend to produce quite a high quality wellbore. So we're using less weight on bit, less deflection that we're being exposed to, less lateral deviation and lateral stability issues. So these work in our favor to make sure that we're delivering a quality wellbore, so less susceptible to spiraling, less drag because we're using less weight on bit. So in short, yes, we do get less drag. We've got some evidence to support that in terms of post-run log analysis as well.
Have you tested with roller cone bits, or has this technology negated the needs for high TCI bits in hard rock?
Yeah, so the answer is no, we haven't. We won't, and we believe the future is in PDC technology for these future gains and for the applications in the hardest and hottest of rocks. Particularly when you're trying, you're at 6,000–7,000 meters and you're trying to stay on bottom.
Can you comment on the use of the tool in an exploration environment where little information is available?
those are the sort of suicide passes that you get for your first runs. So I'm delighted to say that we have been in an exploration environment where there were a great number of unknowns. So yeah, the tool doesn't know what the rocks are. So yeah, we can go in exploration, and we'll happily take what information you have, however scant it may be, and set up the tool to give you the operational flexibility to try and improve your performance. Harder to do a side-by-side comparison, but hey, there's always some data available somewhere.
Here a question that someone noticed, elastomers in the tool. Do you think the high fluid flow rate keeps the tool cool when drilling in hot 200-degree wells?
Any flow rate will help cool. Yeah, we've not been in a situation where we've been involved with mud coolers, but you know, we're quite comfortable operating in these higher temperatures. That's what the tool's been designed for. That's what it's done in the field to date.
That's one of those questions where I don't know the abbreviation, but hope it makes sense. Can it be run with PDM?
It could. The answer is it could. Typically, you would use it only for steering functionality, so we would sit behind it for steering purposes. If someone is asking on the basis of maybe people would understand a performance motor, and you're trying to spin it up or apply high torque, that's not what it's for. It wouldn't help you, it wouldn't give you any further assistance. So can it be run with a PDM? Yes. If you're looking at purely from a performance motor perspective, it's not required. If you're looking at it from a steering objective, yes, that would be one way of doing directional work, and we would sit behind conventionally the PDM itself to allow you to do your steering. Hope that answers.
I hope so too. And then here, and that seems to be the last question. Do you have any data on stick slip mitigation?
Yes, we do. We've covered that before.
Okay, then I'll believe it or not, but I think then we went through all of these questions. It's been a very lively question and answer group here. So I think with that, I think we should, well, now comes some last minute questions. So maybe given that we have a few minutes left.
Just one more thing, as Columbo used to say.
So one more thing. And of course, the question how much you spend on R&D is a question that you might not want to answer, but yeah. But I guess I'll leave it at that unless you jump in. The other thing, what spins the valve?
Okay, so R&D, I think anyone that's been to our facility will understand that we've invested heavily. We've invested not just from a money perspective, but the time and resource. We have a suite of people here. We've got great facilities here in Aberdeen. It's an absolute privilege to work in the environment with the people that we have. And it's been a number of years. So time, people, facilities aren't cheap is probably the best way I can describe that. How do we rotate the valve assembly? We have a non-rotating sleeve, and we index the valve assembly basically by rotating the drill string. So that keeps it static relative rotation. The drill string rotates, and that's what actuates the valve assembly itself. Good question.
Excellent. And I think with that, I join the many comments here that talk about a fantastic and interesting presentation by you and Q&A sessions. Of course, that came also from the one person that asked most of the questions, but fair enough. I'll be sharing some of the contact requests that some of the participants shared here with you, Jamie. In the meantime, I think I thank you, Jamie, for your presentation and your taking the time to answer all those questions. And for the rest of one, we wish you a very good weekend. Thanks for joining us today. And with that, I'll leave you and thank you so much. We're ending the webinar now. Bye-bye.
Thank you, Alex. Thank you, everyone. Have a great weekend.